You ever wonder how your email just knows what's spam? Or how a website decides what movie you should watch next? Well, a lot of that magic comes from a tool called Logistic Regression. Now, it sounds super technical, I know, but it's really all about teaching machines to make simple yes or no decisions. And by the end of this, you're going to see exactly how this one idea powers so much of the world around us. Okay, let's just dive right in. Look at this penguin. For us, it's easy, right? Happy or sad. But for a machine, it just sees data, a bunch of inputs. And based on that data, it has to make a call. It has to put it in a box, happy or sad. This simple act of sorting things into one of two groups, that is the absolute heart of what we're talking about today. It's a huge deal in machine learning. So here's how we're going to break this all down. First, we'll use our penguin to frame the problem. Then we'll see why just drawing a straight line, well, why it totally fails. After that, we'll introduce the hero of our story, this perfect S-curve. We'll get into how that curve lets us talk about probabilities, and finally, we'll see how the machine actually learns from its mistakes to get better. Sound good? Let's do it. All right, first things first. What are we actually trying to do here? In the world of machine learning, we call this a classification problem. And the goal is super simple. We want to teach a machine to look at any piece of information and decide which of two buckets it belongs in. Now, in machine learning speak, we usually label these buckets class 1 and class 0. So class 1 can mean yes, or that a tumor is malignant, or that our penguin is happy. And class 0 is just the opposite, no, benign, or sad. The whole mission is to build a model that can look at brand new data it's never seen before and put it in the right bucket. So the big question is, how do we get a machine to find that dividing line between the two groups? Let's start with the most obvious tool we have, a simple, straight line. Let's use a more serious example for a second, figuring out if a tumor is benign or malignant based on its size. So here on the graph, you can see all the benign cases are down at 0, and the malignant ones are up at 1. The most intuitive thing to do is just draw a line through it, right? We can then pick a cutoff point, say halfway up at 0.5. Anything above that line we'll call malignant. And you know what? At first glance, this actually looks pretty reasonable. But here's the thing. This straight line idea seems okay when all the data is clustered together nicely. But the real world is messy, right? It's never that clean. So what happens when we find something unexpected? A piece of data that's way out there on its own, what we call an outlier. And boom, there's the problem. Look what happened. That one single data point, that one really big tumor, has literally grabbed our line and pulled it way out of whack. And now, our original cutoff point at 0.5 is totally broken. It would now misclassify a bunch of tumors that are actually malignant, which, could be a really big deal. So this really exposes the fatal flaw. Using a straight line, what's called linear regression, it's just too sensitive. It's too fragile for this kind of work. One weird piece of data can come along and just shatter the whole system. We clearly need a better tool for the job. Okay, so we've seen why this simple approach doesn't work. Now it's time to bring in the solution. So let's talk about logistic regression and its secret weapon, the perfect S-curve. I mean, this picture says it all, doesn't it? On the left, you've got our broken, fragile straight line. But on the right, look at that elegant S-shaped curve from logistic regression. See how it hugs the two groups? It flattens out at the top and the bottom. And that's the key. It means those outliers can't just pull it all over the place. Now, this special curve, it's not just a random shape. It has a name. It's called the sigmoid function. And it's not just pretty. It has some very specific mathematical properties that make it absolutely perfect for separating two groups like this. So what makes this curve so great? Well, think of it as having superpowers. First, and this is the most important one, no matter what data you put into it, the answer that comes out is always squished between 0 and 1, which, as we're about to see, is perfect for talking about probability. It's also way less bothered by those pesky outliers. And finally, it gives us a really stable, consistent decision boundary right in the middle. It's basically custom made for this exact problem. Okay, so we have this beautiful S-curve, but what is it actually telling us? This is a really important shift in thinking. Unlike a straight line that could just shoot off to infinity, this S-curve speaks a very specific language, the language of probability. So instead of just spitting out a hard yes or no, the model gives us the probability, the chance that something belongs to class 1. So for our tumor example, it doesn't just say malignant. It says something much more useful, like there is an 85% probability that this tumor is malignant. And once you have that probability, making the final decision is actually super easy. We just set a simple rule, a threshold, usually right at 50% or zero point 0.5. If the model says the probability is more than zero point 0.5, we call it a yes, class 1. If it's less, we call it a no, class 0. It's simple, it's clear, and it's incredibly effective. Okay, this all sounds fantastic. The S-curve is the right tool, and using probability makes a ton of sense. But wait a minute. For any bunch of data, you could draw millions of slightly different S-curves. So how in the world does the machine figure out which one is the absolute best one? This right here is where the learning in machine learning actually kicks in. The model has to have some way to grade itself, to figure out when it's wrong, and then adjust itself to do better next time. So let's just peek under the hood for a second and see how that works. The way it learns is by using a penalty system. It's called a cost function. But the logic is really simple. Look at this table. If the real answer is 1 and the model predicts something close to 1, the cost or penalty is 0. Awesome. But, and this is the cool part, if the real answer is 1 and the model confidently predicts 0, the cost becomes infinite. It gets a massive, massive penalty for being so sure of itself and so wrong. And this graph just shows that penalty system perfectly. Just follow the red curve for a second. That's for when the correct answer is 1. As the model's prediction gets closer and closer to 0, meaning it's getting more and more wrong, you can see that cost just shoots straight up to infinity. The same thing happens in reverse for the other class. It's this extreme penalty that forces the model to get better. And if you're curious about the math behind it, this is the actual equation for that cost function. Now, you totally don't need to memorize this. Just understand that this formula is the clever, mathematical way of writing down that penalty rule we just talked about. This is the engine that makes the whole learning process go. So what's the end game here? The machine's only goal during its training is to try out tons and tons of different S-curves. And for each one, it adds up the total penalty score across all the data points. Its job is to just keep wiggling that curve around until it finds the one single position that has the lowest possible penalty score. That's the winner. That's the curve it keeps. And that really brings us to the most important thing to remember. Logistic regression is not about drawing a line through a bunch of points. That's something else. This is all about finding the best possible boundary that separates one group from another. It's a separator. It's a classifier. So now that you know the secret, think about it. From your email deciding spam or not spam, to a bank deciding approve or deny, to even medical systems helping to spot diseases. This beautifully simple idea of finding a boundary using probability is working all around you all the time. It really just leaves you wondering, what's it going to classify next?